Hello there, and welcome to the Drowsy Scientist channel. Tonight we are drifting into diamonds' quiet brilliance, objects so familiar that we rarely pause to think about how extraordinary they are in real life. These small shining forms carry stories that begin far beneath our feet in places shaped by pressure, time, and patience beyond our wildest dreams. They are signs of devotion and celebration. Yet, they are also records of Earth's deepest processes, waiting silently to be noticed. As we explore this topic together, you may find yourself seeing diamonds differently, not as decorations, but as travelers, survivors, and witnesses to forces that still shape our world. There is something grounding about that thought, the idea that something so calm and steady was born in conditions so intense, and yet emerged with such quiet beauty. If you enjoy these gentle journeys, I invite you to subscribe, like, or comment below. It helps others find their way here too, one sleepy soul at a time. But for the time being, all you need to do is unwind. Let your shoulders relax. Allow your eyes to grow heavy and let your thoughts soften as we wander through this remarkable world together. Let's begin. Volcano-like eruptions can deliver diamond to the surface with astonishing speed. The word eruption makes us think of lava, but diamond delivery is stranger than that. In rare events, gas-rich magma punches upward from deep regions, racing through the crust, so quickly that it can carry solid chunks, like a freight elevator. This speed is crucial. Diamonds are stable only under immense pressure, so a slow rise would give them time to transform into other forms of carbon. Instead, a rapid ascent acts like a rescue mission, preserving crystals that would otherwise be erased. When the eruption ends, it leaves behind a vertical pipe of unusual rock and scattered fragments called xenoliths, pieces of the deep brought to the surface like souvenirs from an unreachable place. Much later, erosion and rivers can spread those diamonds even farther, turning a single violent moment into centuries of quiet discovery. That is why some diamonds are found far from any obvious volcanic mountain. Their journey was not gentle, but their arrival can be, slipping into soil, gravel, and stream beds, waiting for a human hand to notice. Most diamonds are even older than dinosaurs by a lot. Dinosaurs feel ancient to us that a diamond can make them seem recent. Many natural diamonds formed so far back that the continents above them were arranged differently, and the air and oceans were not what we know today. A diamond can exist through eras, when life on land was barely getting started, through periods when ice covered huge portions of the planet, through times when tropical forests grew in places that are deserts now. That endurance gives diamonds a strange emotional weight. They are not just rare, they are patient. Their surfaces may be polished by human hands, but their cores are records of deep time. Even the tiniest crystal can be a relic from a world that no longer exists, carried into our present by a chain of events that had nothing to do with beauty or romance. When someone calls a diamond timeless, it is not only a compliment. It is a literal description of how long it has already been here. A diamond can trap ancient mantle minerals like time capsules. During growth, a diamond can swallow tiny crystals from its surroundings and seal them inside like insects in amber. Except these guests are Earth's deepest minerals. Once trapped, they are protected from weathering, water, and the chemical chaos of the surface. That is what makes them so valuable to science. Many mantle minerals do not survive the journey upward on their own. They change, react, or fall apart. Inside a diamond, they can arrive intact, still carrying the signature of the environment that formed them. Using these inclusions, researchers can learn about temperature, chemistry, and the conditions of deep rock. The diamond as a natural vault. For a viewer, the wonder is simple. A gemstone can be more than pretty. It can be a sealed sample bottle from a region of Earth that no drill has reached. When you look into a clear stone and see a tiny crystal, you are not seeing a floor. You are seeing a preserved fragment of the planet's interior, saved by chance and crystal growth. Those trapped minerals reveal pressures humans cannot create easily. Some inclusions carry a clue that is almost unbelievable. They form at pressures so high that recreating them in a laboratory requires specialized equipment and extreme conditions. When scientists identify certain mineral phases inside diamonds, they are effectively reading a depth gauge. These minerals act like witnesses that cannot lie because their crystal structures only exist when pressure is immense. If the pressure drops, they would normally transform into different forms. The diamond prevents that change by keeping them locked in a tight embrace. That means a tiny inclusion can point to formation zones located hundreds of miles or more below the crust, where Earth's behavior is influenced by the shifting of the planet's internal layers. This is not abstract trivia. Pressure changes how minerals hold water, how rocks flow, and how heat moves, which affects everything from volcanism to the long cycle of continents. A diamond inclusion is a miniature report from that realm. It tells us not just that diamonds are deep, but that some are born in places where matter itself behaves differently. Under pressure, diamonds behave like living light despite being made entirely of carbon. What changes? Everything is the way those carbon atoms lock hands. Each atom in a diamond binds to four neighbors in a rigid, three-dimensional scaffold, more like a perfect architectural truss than a pile of charcoal. That crystal order gives diamond its clarity, its stiffness, and its strange relationship with light. Photons enter, slow down, bend, and ricochet through the interior as if the stone has its own private hall of mirrors. Even when a diamond looks. Nonetheless, the internal physics are active, transforming ordinary illumination into sharp flashes and tiny rainbows. Carbon can also arrange itself as graphite, the soft material in pencils, which makes diamonds feel like a reminder that matter has moods. The same element can, depending on how it decides to connect, it can either write on paper or outlast mountains. A diamond began deep underground long before humans existed. A finished gem can feel like a modern object, but its story starts in darkness, far beneath the continents, where rock behaves more like slow-moving putty than solid ground. There, carbon atoms drift through hot fluids and melts, then settle into. In a place where sunlight has never been, crystals form. What is most unsettling is the timescale. A diamond can spend unimaginable stretches of time resting. While mountain ranges rise above the deep and oceans open and close, we're down and vanish again. It is not waiting for us. It's merely persisting. Only much later does a violent geological event carry it upward where it is discovered by humans who give it a name, a price, and a story. When you grasp a diamond, you are touching a relic from Earth's long, shaped before our own memories. Species had a plan or even a word. Diamonds are the hardest natural mineral, frequently observed on Earth. Hardness is not toughness, and that twist is part of why diamonds are so fascinating. Hardness means resistance to scratching, and diamond sits at the very top of the standard scale used by gemologists because its crystal lattice is so tightly bound. That tightness makes it stubborn against abrasion in a way that feels almost unfair. Diamonds are not just resistant to wear. It forces the world to yield first. This is why tiny diamond grains are used to shape materials that would defeat most tools and why a diamond point can leave a mark where others slide away. However, order is the source of this extreme hardness, not invincibility. The same internal perfection that makes diamonds so scratch-resistant also creates directional weak planes like hidden seams in a fortress. The hardest common mineral was created by nature beautifully and quietly, leaving it with one precise way to fail. Some diamonds formed more than 100 m underground. That depth is not just a distance. It is a different kind of world. Pressure rises far below the surface until rock forms. Behaves in ways that defy everyday intuition. Cracks narrow, minerals rearrange, and fluids move through stone like whispers through a wall. In that environment, diamond becomes the preferred form of carbon and crystal growth can begin. What makes this fascinating is the journey required to bring such a stone upward. Diamonds do not migrate slowly to the surface like bubbles. A quick geological elevator is needed for them. A violent event that tears through layers of earth and carries fragments upward before the crystals can change back into softer carbon forms. If the trip is too slow, the diamond can lose its identity. So each deep-formed diamond is evidence of both creation and escape. It was born in crushing pressure, then saved by speed. When you see one glittering under room light, you are seeing something that should never have been visible at all, except that Earth briefly moved fast enough to deliver it. One diamond can scratch nearly every other gemstone you know. Scratching is a simple test with a dramatic lesson. When two minerals meet, the harder one plows microscopic grooves into the softer one, leaving damage that never truly disappears. Diamond usually comes out on top in that contest because of its atoms are locked into a structure that refuses to be carved by most rivals. This is why careful jewelers store diamonds separately, even from other precious stones. A loose diamond can quietly scar sapphires, rubies, and emeralds just by sharing a pouch. It is also why diamond polishing is such a specialized craft. To shape a diamond, due to the fact that the material is, other diamonds typically need to be ground into powder, essentially asking to be worked by its own kind. There is something almost mythic about that. A stone that can mark almost everything else is in practice, most easily shaped by a chorus of its own dust, patiently wearing it into brilliance. A diamond can survive fire, but it can still burn. Diamonds feel eternal, so it surprises many people too. Learn they are not immune to destruction. In everyday conditions, they are stable, but under intense heat, especially in the presence of oxygen, diamond can oxidize. Simply put, it can catch fire. The reason is simple and unsettling. A diamond is carbon, and carbon can react with oxygen when the temperature is high enough. That does not mean a candle with a razor ring, but it does mean that jewelry can be damaged by extreme heat in a workshop fire, a torch accident, or careless repair. Even when a diamond does not fully burn, heat can cause changes that affect appearance. Metal settings can warp, stress can travel through the stone, and tiny fractures can worsen. Respect, not fear, is the lesson. Diamond's reputation comes from what it resists, but its chemistry still belongs to the same world as charcoal and smoke, with the same fundamental rules quietly applying. River gravels can hide. Diamonds carried far from their birthplace. Some of the most famous diamond finds did not come from hard rock mining at all. They emerged from calm water. Over long stretches of time, rain, wind, and flowing rivers break down diamond-bearing rocks and sweep the tougher fragments downstream. Diamonds, dense and durable, can settle into natural traps. The inside bends of rivers, gravel bars, and ancient stream beds now far from any running water. This is why a person can discover a diamond in sediment with no obvious pipe nearby. The original source may be many miles away, worn down and disguised by erosion. These deposits can be wonderfully deceptive. A river can sort and concentrate stones the way careful hand might, turning a scattered supply into a pocket of treasure. It also creates mystery. If you find diamonds in gravel, the next question is not just where they are, but where they came from. The landscape becomes a detective story written in pebbles, currents, and time. A diamond's growth can happen in pulses, not one moment. It is tempting to imagine a diamond forming like a single magical event, but many do not grow that way. Growth can start, pause, and start again depending on whether the surrounding conditions provide carbonary fluids or the right chemistry for crystal building. These episodes can leave subtle internal boundaries like chapters where one phase of growth ended and another began later. The result is a stone that is not just old but complicated, with a history of changing circumstances written into its interior. This makes diamonds feel less like static objects and more like records of shifting environments deep underground. One pulse could occur during a period of movement of the mantle fluid, another during a subsequent event that brought carbon and pressure conditions that favored diamond. Again, the pauses matter as much as the growth because they hint at a deep world that is not constant. When you see a diamond as something that assembled itself over time in fits and starts, it becomes easier to feel the planet as active, even in places we call solid. Diamonds can serve as timelines rather than snapshots. Many diamonds grow as crystals, but some grows twins. Crystal twins are one of nature's most elegant shortcuts. Instead of a single orderly crystal expanding smoothly, two parts of the diamond grow together in a specific mirrored relationship, locked into each other's orientation. This can create unusual shapes and internal patterns that are not mistakes, but expressions of how the crystal found a stable way to expand under its conditions. Twinning can also influence how a diamond behaves when it is cut. A cutter may discover that the stone has directional quirks, subtle variations in strain or growth behavior that require different planning than a simple crystal. The interest for viewers is in the idea of identity. Two diamonds can be the same material formed under similar pressures, but one is a simple crystal and the other is a pair that grew in collaboration with itself. It is like finding two versions of the same story. One is written in a single clean line. The other is written in mirrored paragraphs that meet in the middle. Twinning reminds us that even in the deep earth, growth is not always uniform. Sometimes it is cooperative, symmetrical, and strange in the most beautiful way. A diamond's entire character can be determined by a single flaw. Perfection is not always the most interesting thing in nature, and diamonds prove it. Inside, many stones are tiny features, a minuscule crystal trapped during growth, a faint internal line, a cloud of microscopic pinpoints. These are not always damage. They can be fingerprints of formation, clues about the environment that built the stone. And yet, the market treats them as destiny. A nearly invisible inclusion can change a grade, shift a price, and decide whether a diamond becomes the centerpiece of a ring or disappears into an industrial tool. Even when you cannot see the feature without magnification, it can change how light moves through the crystal, subtly affecting the diamond's look. There is also a human story here. People often fall in love with the idea of flawless, but many collectors prefer stones with distinctive quirks because they feel like individuals, not copies. A diamond's personality is not always about being pure. It is about being specific. A tiny internal detail can turn a stone into a one-of-one. Most diamonds contain inclusions, tiny internal features from formation. What many people call imperfections are often the most honest parts of the stone. Inclusions in a diamond can appear as pinpoints, clouds, faint lines, or tiny shapes that seem like they were drawn with a single careful touch. These features are not decorations added later. They are the record of a crystal growing in a real environment where the world does not pause for the sake of beauty. Inclusions can also change how a diamond feels to the eye, making it look softer, brighter, or more complex depending on where they sit and how light interacts with them. Some are so small they only appear under magnification, yet they still influence the diamond's character, almost like a hidden accent in a voice. The most captivating part is that inclusions make each stone repeatable. Even diamonds with the same shape and weight can be distinguished by their internal landscape. It turns a gemstone into a document, not a second copy. Some inclusions are other crystals locked inside forever. Sometimes a diamond carries a guest, and that guest has a name, a shape, and its own story. Under magnification, you can see tiny crystals inside, complete sharp edges, colors, and reflective faces like a miniature museum exhibit, sealed behind glass. These are not stains or surface marks. They are separate minerals that were present during growth and became enclosed as the diamond expanded around them. This is a rare kind of intimacy in geology. One crystal literally wrapping another and keeping it unchanged while the world above transforms. For gemologists, these trapped crystals can help identify origin and growth conditions. For anyone else, they offer a more personal thrill. You are not just looking at a gem. You are looking at a stone that contains another stone, perfectly preserved, impossible to remove without destroying the whole. It is a reminder that diamonds are not only objects of sparkle. They are containers, capable of holding a private secret for a span of time that makes human history feel brief. The famous 4C's grade. Diamonds. Cut, color, clarity, carat. These 4 categories sound simple, but they are really 4 different ways of describing how a diamond behaves in the real world. Cut is performance, the way the stone handles light. Color is mood, the subtle temperature of its appearance. Clarity is identity, the presence of internal features that make it unique or make it cleaner. Carat is weight, the physical amount of diamond you are carrying. What makes the 4C's captivating is that they constantly trade against each other. A heavier stone might be less lively if the cut is compromised to keep weight. A very clean stone might still look dull if the proportions waste light. A slightly warm Color can look beautiful in the right setting and lighting, while a colder stone can feel sharper and more formal. The 4Cs do not function as scoreboards. They are a set of levers. Changing one often changes how the others matter. Understanding them turns diamond shopping from guessing into noticing, because you start to see what your eyes respond to and why. Carat is a weight unit, not a size promise. Carat sounds like it should describe how big a diamond looks, but it only tells you mass. Two stones with the same carat weight can appear very different in size because of shape, cup proportions, and how the depth affects the distribution of weight. Too deep of a diamond cut can conceal weight where you cannot see it, leaving a smaller face-up look than you expected. A well-proportioned stone can spread its weight in a way that reads larger from above, even without adding mass. This is why experienced buyers talk about millimeter measurements and face-up dimensions, not only carat. It is also why certain shapes can look larger for the same weight simply because their outlines cover more surface area. The fascination is that carat is a number that feels emotionally powerful. However, weight cannot be directly read by the eye. The eye detects presence, brightness, and area. The carat reveals who you are holding. Cut reveals the actual sights you'll see. Two diamonds can share carat weight, yet look wildly different. Imagine two identically sized stones, yet one seems to command the room and the other seems modest. This can happen because visual impact depends on more than mass. A shallow stone can look wide, but could lose its brightness if light escapes. A deeper stone can look smaller from above, but may appear darker or more concentrated in its pattern. Shape matters, too. An elongated oval spreads across a finger differently than a round, changing the sense of scale, even at equal weight. And then there is the subtle influence of edge thickness, girdle choices, and how high the stone sips in its setting. All of this means carat is only one part of the story of appearance. The same weight can wear like two different personalities, one restraint and one boldness. This is why diamonds are such persuasive objects. They make you confront how perception works. We believe we are seeing size, but we are really seeing geometry, light behavior, and proportions working together. A diamond can teach your eyes to become more honest about what they value. Clarity grades judge internal features, not the diamond's beauty alone. A clarity grade is a careful description of what can be seen inside a diamond under standardized magnification and lighting. It is not a direct measure of how gorgeous the stone will feel to someone who is simply enjoying it. Many inclusions are invisible without a loupe, especially once the diamond is set and moving in everyday light. Others can be visible, but still not ugly, depending on where they sit and how they interact with reflection. This is where clarity becomes a little philosophical. A high clarity grade can be thrilling because it feels pure and clean, but a slightly lower grade can still look stunning, and sometimes it offers more character for less cost. The grade as well cannot predict style preferences. Some people love the idea of near flawless. Others care more about brightness and cut. Clarity is best understood as a map of internal landmarks, not a final verdict on beauty. A diamond is a performance piece and clarity is only one note in the music. Many diamonds travel upward inside rare rocks called kimberlite. Kimberlite is less like ordinary volcanic rock and more like a geological courier built for speed and surprise. It forms deep enough to pick up diamonds and odd fragments of the mantle, then rises in a rush that cracks the crust like a sudden heartbeat. When it reaches a carat-shaped pipe or a vertical path where the rock cooled in place can remain on the surface. What makes this so captivating is how specific the conditions are. Most magma would melt, damage, or simply fail to carry diamonds at all. Kimberlite is unusually rich in gases and volatiles, which helps it move fast and tear loose passengers along the way. That is why a kimberlite pipe is not just a deposit. It tells the story of transport. Miners are not digging for a gemstone alone. They are excavating the remains of a rare earth event that briefly connected the deep interior to open air. Some diamonds are brought in via lamprey, a different deep eruption route. Lamprey is the quieter cousin that still carries astonishing gifts. It is rarer than kimberlite, and it forms from a melt, with a unique recipe frequently high in potassium and other elements that interest geologists. When lamproyer erupts, it can deliver diamonds too, but the clues it leaves behind do not look the same. The shapes of the pipes may vary. The minerals in the rock are distinctive, and the regions that host lampro can be unexpected. This matters because it changes how humans search. Entire diamond. Discoveries have happened because someone recognized the fingerprint of lamprite and realized the ground was whispering a different kind of possibility. There is something thrilling about that. Two separate deep pathways can lead to the same glittering result, like two hidden doors into the same underground vault. And because lampro occurrences are uncommon, every diamond found this way feels like evidence of a rare and specialized journey that Earth does not perform often. Diamonds can form Earth's mantle, not the crust. The crust is where we live, but it is not where most diamonds are born. Their origin is deeper in the mantle, a vast region of hot rock that slowly circulates beneath continents. In this hidden world, pressure is strong, enough that carbon prefers to lock into diamond rather than remain in other forms. That fact alone changes how you think about Earth. The mantle is not a silent layer. It is an engine room moving heat, shifting continents, and storing chemical stories from earlier chapters of the planet. When a diamond forms there, it is not growing in a neat cavity like a geode. It is crystallizing in an environment that can include fluids, melts, and shifting conditions, all under crushing pressure. Because of this, a diamond is no longer just a gem, but rather a message from a place we will never visit directly. The mantle rarely speaks to us in solid objects. Diamonds are among the few times it does. Some diamonds contain water-bearing minerals from deep earth. Water seems like a superficial narrative, but deep earth can hide it in unexpected ways. Some diamonds contain inclusions of minerals that hold water within their structure, not as liquid droplets, but as hydroxyl groups tucked into crystal lattices. This is thrilling because it hints at vast hidden reservoirs. Water, locked into rock far below ocean clouds. When those minerals are found, they suggest that water can travel deep through subduction within diamonds and be stored in mantle regions for very long times. That changes the mood of the planet. Earth is not simply a wet surface wrapped around dry rock. It may be a world that cycles water through its interior using pressure and mineral chemistry as storage. The diamond becomes a messenger again, carrying proof that deep rock can keep water in forms we do not see. For the listener, it comes as a light shock. The same gem people prize for sparkle can also be a clue that Earth's water story has chapters far beneath our feet, written in minerals and locked away until a diamond arrives to reveal them. Certain diamonds prove parts of the mantle recycle old ocean crust. There is a chemical accent in some diamonds, but it does not sound like the deep mantle at all. They're carbon and trapped. Minerals can show signatures consistent with material that once lived at the surface, then traveled downward with tectonic plates subduct. In other words, pieces of ocean crust, altered by seawater and life, can be pulled into the deep and eventually become part of the environment where diamonds grow. That is a staggering loop. It means the mantle is not an untouched abyss. It is a mixing bowl that can receive ingredients from the surface and hold them long enough to reshape them. Diamonds in this sense are not just deep objects. They are proof of recycling on a planetary scale. A stone worn on a finger can carry echoes of ancient seafloor pushed down through the Earth's conveyor belt and under pressure changed into something completely new. It also adds emotion to geology. The planet does not discard. It repurposes. Diamonds can be the end of a journey that began with waves and basalt, then disappeared into darkness, only to return as a crystal that catches light. The sparkle comes from light bouncing inside, not surface shine. A diamond's magic is not a glossy coat. It is a carefully engineered escape trick. Light enters the stone and hits internal surfaces at angles that make it bounce back inward instead of leaking out. With the right geometry, those bounces send light ricocheting around until it finally bursts back through the top in bright flashes. This is why the same rough crystal can look dull in one cut and breathtaking in another. The cutter is not decorating the surface. They are designing a pathway for trapped light. That is also why a diamond that is too deep can look dark and one that is too shallow can look watery. The equilibrium is delicate and it turns the gem into a tiny optical machine. When people say a diamond sparkles, they are really noticing a choreography of angles. It is less like paint and more like architecture built to make light do something it would not normally do. Perfect detailer diamonds are rarer than most people assume. Clarity is a strange kind of rarity, because it is not about size or color. It is about what did not happen. Deep, underground, a diamond is growing in an environment full of opportunities for interruptions, stray crystals, tiny changes in chemicals and fractures. A truly clean interior means the diamond managed to form without much of its surroundings being swallowed up and without being stressed in such a way that it was visible. Marks. Because of this, even the most transparent stones can appear to be almost unreal, like window cut from solid time. But the most interesting part is how quickly the idea of perfect can collapse into human limits. Two people can look at the same stone and see different things depending on lighting, magnification, and experience. Clarity extends beyond geology. It's about perception. When you realize how many chances there, a clear diamond stops to feel like a diamond if it carried evidence of its past. An improbable quiet victory, not just a pretty purchase. A feather inclusion. Looks delicate, yet it is trapped stone. The name sounds gentle, but the reality is pure geology. A feather inclusion is a tiny internal fracture that reflects light in a way that can resemble a soft, wispy shape. It is not a floating strand. It's a frozen crack that usually forms when the crystal goes through stress during its long life underground or during the violent trip upward. What? The contrast between its appearance and meaning is what makes it so fascinating. The feature can look airy and harmless, yet it represents the moment the diamond was pushed beyond comfort, then survived. Anyway, depending on its size and location, a feather can make a stone look or feel completely different. Handles during cutting and setting. That gives it tension, like a quiet fault line. In some diamonds, a feather becomes a signature mark, a detail that helps experts recognize the stone again later, almost like a birthmark. It is proof that diamonds are not only built by calm growth, but also by strain, pressure shifts, and recovery. Diamonds can show internal graining like growth rings in wood. Even when a diamond looks perfectly smooth, the inside, certain lighting conditions can reveal a subtle texture, banding, or directional pattern. This internal graining comes from the way the crystal grew, sometimes with tiny changes in chemistry, sometimes with slight distortions in the lattice as it expanded. Because it can be so subtle, it feels like the diamond is hiding its handwriting, only showing it when you know how to look. Graining matters, because it can influence brilliance and clarity in ways that are not obvious at first glance. It can also affect how the stone responds to cutting and polishing, since different directions can behave differently under the wheel. What it suggests about time is the most compelling part. Graining is a visible trace of change during formation, a reminder that growth was not perfectly uniform, and that the environment evolved while the diamond did. It turns a gem into a biography, not just a crystal. You are seeing the diamond's memory of its own, becoming written as lines inside solid carbon. Some diamonds glow under ultraviolet light, called fluorescence. In the right conditions, a diamond can surprise you by answering light with light. Under ultraviolet, certain stones emit a visible glow, often blue, sometimes other shades, as if the diamond is briefly revealing a hidden personality. This is the result of particular flaws or trace elements in the crystal that absorb ultraviolet energy and remit it at different wavelengths. The effect can be subtle or dramatic, and it can change how a diamond looks in everyday life, especially in sunlight where ultraviolet is present. For some stones, fluorescence can make the diamond appear whiter and brighter, almost like a secret advantage. Rarely, it may cause the stone to appear slightly hazy, which is why it becomes part of careful evaluation. What makes fluorescent so captivating is that it turns a gemstone into a responsive object, not a passive one. The diamond is not simply reflecting the world. It is converting energy and sending it back in its own voice. Once you have seen a diamond glow, it is hard to believe it is only an ornament. A few diamonds keep glowing after light stops. Phosphorescence. This is where diamonds start to feel almost uncanny. In rare cases, a diamond continues to emit light after the ultraviolet source is removed, holding on to energy and releasing it slowly. That lingering glow is phosphorescence, and it can last for moments to longer depending on the stone's internal structure and the nature of its defects. It is not a superficial ploy. The effect comes from the way electrons get temporarily trapped in the crystal, then return to their normal states over time, releasing light as they do. Some diamonds are known for this behavior in a way that becomes part of their identity, almost like a signature that only appears in darkness. For a viewer, the wonder is immediate. A gemstone that keeps glowing feels like it is refusing to end the scene. It adds a new dimension to what a diamond can be, shifting it from sparkle to afterglow, from reflection to memory. The stone briefly becomes its own light source, then gradually returns to silence, as if it was breathing out the last of a hidden charge. Blue diamonds often owe their color to boron atoms. Blue diamonds are not painted by the sky. They are altered by chemistry. In these stones, tiny amounts of boron can slip into the carbon lattice during growth, changing how the diamond absorbs light and leaving behind a blue hue that can range from soft to strikingly intense. What makes this especially fascinating is that boron does more than tint the gem. It can also change the diamond's electrical behavior, giving some blue diamonds properties that ordinary diamonds do not share. That means the color is not merely visual. It is physical proof that the crystal formed in an environment where boron was available and able to join the structure. The result is a gemstone that carries a trace of its birthplace, like an accent you cannot remove. Blue diamonds have also gathered an outsized cultural reputation, partly because they are rare and partly because they look like something you would not expect from carbon. When you learn the color comes from a few borrowed atoms, the wonder deepens. A minor alteration can alter the text, the entire identity of a stone. Yellow diamonds usually get their color from nitrogen atoms. Yellow is often the most approachable diamond color, warm and unmistakable. Yet, its cause is surprisingly specific. Nitrogen atoms can replace or cluster among carbon atoms in the crystal, altering which wavelengths of light the diamond absorbs. The stone then returns the remaining light with a yellow tone that can be pale, vivid, or even with a lot of color. What makes this compelling is that nitrogen is one of the most common impurities in diamonds, which means yellow can be a kind of natural signature of how the diamond grew. The arrangement matters. Nitrogen scattered one way can create one kind of color, while grouped differently, it can change the shade and intensity. So the diamond's yellow is not just a color. It is a pattern, a structural choice locked into the crystal. For a viewer, this transforms yellow from a simple hue into a clue. The stone is quietly telling you something about its formation, conditions, its growth history, and the chemistry of the deep environment. It is warmth with a backstory, some light explained by atoms. Pink diamonds can come from crystal lattice distortion, not pigment. Pink diamonds feel like they should be stained by some hidden dye, but their color can arise from stress. In certain stones, the carbon lattice becomes distorted during formation or later deformation, creating subtle changes in how the crystal interacts with light. The result is pink, sometimes soft and delicate, sometimes so strong it feels impossible for a diamond, because it does not involve adding an element. This is one of the most captivating color stories. It is about bending the structure itself. Because it was internally pushed, shifted, and changed, the diamond turns pink. Yet, it kept growing or kept surviving. In that sense, the color is a scar that turned into beauty. It also explains why pink diamonds can be so rare and prized. The conditions that create the right distortion without destroying the crystal are not common. For the listener, it reframes the idea of color as biography. The stone is not merely colored. It has been shaped by pressure and strain in a way that permanently changed how it speaks to light. Green diamonds can be colored by natural radiation over time. In some stones, the green is not a dye and not a mineral impurity. It is a change to the diamond's outer crystal caused by radiation from surrounding rocks, often over very long periods. The effect can be so shallow that cutting or polishing removes it, which is why true green can be rare and why some green diamonds show color concentrated near the surface. When the color survives, it can appear as patches, skins, or delicate zones that hint at where the diamond rested underground after its violent arrival. It is a strange thought that a diamond can be shaped twice. It was formed first by a great deal of pressure and then by an invisible energy that later touched it. This makes green diamonds feel like layered histories, a gemstone with a second chapter written after birth. In the best examples, that green becomes proof that the diamond spent quiet time in the earth, absorbing a faint environmental signature, like a stone keeping a memory of its own burial. Brown diamonds can reflect intense deformation deep underground. Brown diamonds often carry their color, like a record of stress rather than a simple tint. Deep inside the earth, a diamond can be squeezed, shifted, and bent at the atomic scale without breaking apart. That internal distortion changes how the crystal absorbs and transmits light, bringing out tones that can look like honey, cognac, or deep chocolate depending on strength and structure. There were a lot of brown stones were undervalued, partly because people chased icy whiteness. But they are among the most honest storytellers. Their color might be a sign of movement deep in the earth, like a fingerprint, that a diamond is not always born in calm conditions. Some brown diamonds also show complex optical effects with flashes that feel warmer and moodier than a colorless stone. They can make you rethink what beauty means in gems. Instead of pretending that, brown diamonds quietly acknowledge that they were pushed hard, changed by pressure, and still emerged from the earth's gentleness. Intact, retaining that experience in the form of color. Diamonds without color are not color. Free, just balanced to our eyes. A truly perfect absence of color is rarer than most people realize because almost every diamond has some subtle absorption that nudges it toward a faint tint. What we call colorless is frequently a diamond whose minor biases cancel out sufficiently to make the eye reads it as clear, especially when it is viewed face up in a setting designed to flatter it. Professional grading is done under controlled lighting and against reference stones because ordinary environments can hide or exaggerate warmth. Even the metal around a diamond can change what you perceive with yellow-gold lending richness and white metals sharpening the impression of coolness. This makes color feel less like a fixed trait and more like a conversation between crystal and observer. A diamond that looks icy in one room can look slightly creamy in another. Not because it changed, but because your eyes and the light did. The wonder is that colorlessness is often an illusion achieved by balance, not a total void. And that balance is part of what makes these stones feel so clean and quiet. Some diamonds show a rare effect called color change under lighting. A few diamonds behave like they have two identities, shifting their apparent color when the light source changes. Under daylight or fluorescent light, they may lean one way. Then, under warmer indoor lighting, they can tilt toward a different hue. The reason lies in the way the stone takes in certain substances of the spectrum and how different bulbs feed the diamond different mixes of wavelengths. Your eyes also play a role because human color perception adapts to its surroundings. So the same stone can feel, when the room changes, new tint. This effect is uncommon, and when it appears, it can naturally give a diamond the appearance of almost being alive, as if it is responding, rather than simply reflecting. It also creates a quiet kind of suspense. You do not fully know the stone until you have seen it in multiple places. Morning light, evening light, and everything in between. A color change diamond is less like a fixed object and more like a small performance revealed only as the lighting shifts. The term diamond comes from a Greek word meaning unbreakable. The name itself carries a promise. The Greek word for diamond, adamas, was used to describe something unconquerable or unbreakable. And it makes sense that people reached for that language when they encountered a stone that resisted their tools. Long before anyone understood crystal lattices or carbon chemistry, hardness was a kind of magic you could feel with your hands. A material that would not scratch, that kept its edge, that seemed to ignore damage. Naturally attracted words about permanence and power. The fascinating part is that a name can shape culture. Calling a stone unbreakable nudges it into the role of symbol for loyalty, endurance, and status, even when the physical reality is more nuanced. An observation can become a legend through language. And once a legend exists, it can travel farther than any gemstone. The name diamond does not just label the mineral. It frames how humans have imagined it for centuries as something that stands against time and refuses to yield. Ancient Indians traded diamonds long before Europe understood them. For a long time, the world's best-known diamonds came from India, and people there valued them when much of Europe still had little direct access or context for what the stones were. Diamonds moved through trade networks as rare portable wealth, traveling with merchants and changing hands in courts, where gemstones were part of diplomacy and status. In early uses, diamonds were not always cut for sparkle the way we expect today. They could be treasured as natural crystals that are prized for their rarity, hardness, and strange way they catch water light even without modern faceting. India's role also shaped early stories about diamonds, mixing practical trade with mythic ideas about protection and power. What makes this captivating is the sense of time travel. The diamond in a modern ring is part of a much older human habit, the urge to carry a piece of earth that feels special and to let it speak for you. Long before global branding, diamonds were already global, objects moving by human desire and human roots across continents. Brazil once overtook India as a major diamond source. When diamonds were discovered in Brazil, the map of the diamond world shifted. Supply routes changed, fortunes moved, and the idea of where diamonds came from expanded beyond the older assumption that India was the central source. Brazil's deposits included stones found in river gravels and other secondary environments, which helped fuel rushes where people searched sediments instead of tunneling into bedrock. That change mattered because it altered how diamond hunting looked and felt. It became tied to landscapes of rivers and valleys, to labor and speculation, to the belief that wealth might be waiting in the next pan of gravel. The broader impact was cultural too. As new sources emerged, diamonds became less mysterious as a concept and more integrated into global trade with growing systems for sorting, selling, and moving stones across oceans. Brazil's rise is a reminder that diamonds are not only geological, they are historical, reshaping economies and expectations the moment a new region proves it can produce them. A single discovery can relocate an entire industry's attention. South Africa's discoveries reshaped the global diamond industry. When major diamond finds erupted into public awareness in South Africa, the scale of diamond production and the structure of the business transformed. Mining shifted toward large operations. Built on kimberlite pipes, diamonds became something from which huge quantities could be extracted in comparison to many earlier sources. That abundance created a new challenge. If diamonds became too common, their aura of rarity could weaken. The industry responded by constructing modern systems of distribution, sorting, and supply control over the long term alongside powerful messaging that linked diamonds to life milestones. This is where diamond history becomes both industrial and psychological. The stones were still rare in an individual sense, but the flow of them into the market became managed, shaped by logistics, finance, and carefully constructed meaning. South Africa's role is also a reminder that a diamond rush is not just people digging. It is infrastructure, labor, power, and the creation of entire towns and networks around a single resource. Diamonds did not only change jewelry. They changed how desire, scarcity, and story could be used to organize a global commodity. Botswana's diamond wealth transformed its modern economy. Botswana is often mentioned because diamonds became a major pillar of national revenue and helped fund development in ways that stand out in the region. Instead of the resource simply vanishing into private hands, diamond income has been tied to public spending and long-term planning, including investments in health, education, and infrastructure. The result is not a fairy tale with no problems, but it is widely seen as a case where governance choices shaped how resource wealth affected a country. That is what makes the story so compelling. For a viewer, a gemstone can be more than personal luxury. It can become a lever for national change depending on policies, partnerships, and how money is managed over decades. Botswana's diamonds also complicate the way people talk about mining, because the impact is not one single narrative. It can include hard realities and ethical questions, and also genuine economic transformation. As a constant reminder, The diamond resources are not destiny. The outcomes depend on human decisions, and those decisions can echo through generations. Canada produces diamonds from far northern mines in ancient rock. Canada's diamond story feels different because of geography. Many Canadian diamonds come from remote northern regions where mining happens in landscapes defined by cold, distant, and short construction seasons. The diamonds are hosted in very old crust rocks, and the mines operate with heavy logistics, moving supplies across ice roads or by air, planning around weather that can turn simple tasks into major power operations. This setting changes the public image of diamonds. Instead of tropical reveres or desert mines, the backdrop can be tundra and boreal forest with strict environmental planning and close attention to wildlife and water. Canadian diamonds also help popularize modern tracking and certification programs, partly because the supply chain was easier to document from a smaller number of operations. For many buyers, Canada introduced a new kind of diamond origin story, one tied to cold landscapes and a sense of regulated transparency. It is fascinating to realize that the same crystal that formed deep underground can appear in locations that have an almost otherworldly atmosphere before traveling to city jewelry counters thousands of miles away. Diamonds are tracked by ethical sourcing efforts. From mine to market, because diamonds are small, valuable, and easy to move, their supply chains can be complicated. And that complexity is exactly what ethical sourcing tries to reduce. Tracking efforts can include sealed parcels, documented transfers, audits, and chain of custody paperwork designed to keep stones linked to their origin as they travel through cutting, trading, and retail. Some systems also rely on inscriptions, digital records, and independent verification to strengthen confidence. The goal is not perfect purity of history, which is hard in any global commodity, but improved transparency so buyers can make informed choices. What makes this interesting is how modern the diamond world has become. The romance of a gemstone now lives alongside compliance, traceability, and data because consumers and regulators have demanded clearer answers about labor conditions and conflict financing. Ethical sourcing is also a reminder that diamonds are not only geology, they are human networks. If you want a diamond to carry a story you feel good about, the story has to be documented, not assumed. Tracking turns a stone into a traceable object with a paper trail, and that paper trail becomes part of its value. Diamonds grown in laboratories can lower mining impacts. However, energy decisions still matter. Lab-grown diamonds can avoid some impacts associated with mining, such as large-scale excavation and the disturbances that come with it. But the environmental story does not automatically become simple because growing diamonds requires energy, and the climate impact depends heavily on how that electricity is generated. A lab powered by the carbon grids, or the environmental impact of renewable energy sources, can vary greatly from that of those powered by fossil fuels. There are also other inputs like equipment, gases, and the broader manufacturing supply chain, which means responsible production is about more than the crystal itself. This is what makes the topic worth exploring. It is not a clean binary of good versus bad. It's a set of trade-offs that depend on where you are, who watches, and transparency. For viewers, the hook is that diamonds have entered the world of modern sustainability debates where origin is not only romantic, it is measurable. The decision becomes more about the impacts you want to support rather than what appears real. In that sense, lab-grown diamonds are not just a product. They are a new chapter in how humans decide what value should mean. Every diamond is a pressure-borne record of Earth's deep interior. A diamond is one of the few objects you can hold that formed in a realm where the planet is still actively reshaping itself. It began as carbon subjected to intense pressure, arranged into a crystal that can preserve clues about its environment far better than most rocks do. Even when a diamond looks simple, it carries silent information in its growth features, its trace chemistry, and the tiny stresses locked into its structure. That makes it more than a beautiful stone. It is a durable messenger from depth, a physical sample of conditions that shape continents and volcanism, yet remain unreachable to our bodies. What elevates this is the contrast between scale and intimacy. Earth's interior is vast, hot, and slow. moving, while a diamond can sit on a fingertip. And still, the fingertip is holding something made by the same forces that drive the planet's long rhythms. When you see diamonds this way, the fascination expands. The sparkle becomes secondary. The real wonder is that the Earth managed to send you a record of its hidden world, and you can carry it quietly through an ordinary day. Diamonds also have strong dispersion, splitting light into colors. Diamonds are able to display the tiny flashes of red, green, and blue that appear to be tiny surprises due to dispersion. It happens because different wavelengths of light bend by different amounts inside the crystal. So white light can separate into colors as it travels and reflects. Not every diamond shows the same amount of this fire because the cut affects the way and location at which the colored rays exit the stone. A design with certain crown heights and facet arrangements can emphasize dispersion, while other choices favor brightness and contrast. Instead, this creates a fascinating trade. A diamond can be optimized for white brilliance, or it can be tuned to show more colored fire and the best balance. Depends on taste and lighting. Some people want a stone that looks bright in every situation. Others chase those colorful flashes that appear like brief signals. Dispersion also helps explain why diamonds can look different under different bulbs since the spectrum of the light source changes. What colors are available to split? The wonder is that a diamond can act like a tiny prism without ever looking like a prism, hiding that physics inside beauty. A diamond's cut creates brilliance, not the diamond itself. Two diamonds can come from similar rough and still feel like different worlds once they are shaped. The cut decides how light enters, where it travels, and whether it returns to your eye as bright flashes or leaks away unseen. This is why gem professionals talk about proportion, angles, and light performance as if they are personality traits. A cutter is making choices that trade weight for beauty, deciding whether to make a stone livelier or keep it heavier. A well-planned cut can make a smaller diamond look more radiant than a larger one with poor geometry because the eye responds to brightness and contrast more than mass. This is also where human skill becomes part of nature's story. The Earth provides the crystal, but the cut decides how it speaks in light. When you see a diamond that looks awake, it is not only because it formed deep underground. It is because someone shaped it with an understanding of optics, symmetry, and restraint, turning raw potential into visible energy. Poor cutting can make an amazing diamond look sleepy. Every aspect of a diamond can be of high quality and still look dull if the cut wastes light. When proportions are off, the stone can develop problems with famous nicknames. A window is an area that looks transparent instead of bright, as if you can see through the diamond rather than into it. A nail head is a dark center that robs the stone of sparkle. A fisheye can create a washed ring that makes the diamond feel flat. None of these flaws require a bad diamond. They come from geometry. This is why cut is often the most unforgiving factor because you cannot polish your way out of it later. Once the shape is set, the light performance is largely locked in. The most dramatic part is that many casual viewers do not know what they are seeing. They simply feel the lack of life. Their eyes drift away without understanding why. A beautifully cut diamond holds attention because it creates crisp contrast and bright return that the brain reads as energy. Poor cutting does the opposite. Even when the content ought to be better, the round, brilliant cut was designed to maximize light return. The round brilliant is not just popular, it is engineered. Its shape allows many facets to work together, so light is gathered, redirected, and returned in a pattern that feels bright from multiple angles. That design did not appear by accident. It was refined over time as cutters and researchers experimented with proportions, looking for a balance between brightness, flashes, and rainbow fire. The round outline also has practical advantages because it is efficient to rotate during polishing, and it evenly distributes stress for daily wear. But its real power is visual reliability. In many lighting environments, from daylight to a single lamp, a good round brilliant still performs, which is why it became the default image in people's minds when they think of a diamond. It is a cat that tries to be consistently impressive rather than occasionally perfect. When someone says diamond sparkle, they're often picturing this design, a circular arrangement of facets. built to catch light quickly and return it with strong contrast. It is the result of generations of craft turning into a kind of standard language for brilliance. Step cuts trade sparkle for calm mirror-like flashes. A step-cut diamond does not try to glitter constantly. Instead, it creates broad, clean reflections that slide across the stone, like quiet panels of light. Famous examples of built include emerald and astra cuts, with long, straight facets arranged in steps. The effect can feel architectural, almost like looking into a deep hallway lined with mirrors. This makes step cuts unforgiving in a different way. They do not hide internal features easily, so clarity becomes more visible, and the cutter's precision is exposed in every line. A tiny mismatch can break the rhythm. When a step cut is done well, it feels poised and intentional, with flashes that come less often but arrive with authority. It can be the difference between a stone that chats constantly and a stone that speaks only when it has something to say. For many people, that calm is the appeal. It is a diamond style that invites you to stare, not because it overwhelms you with sparkle, but because it offers depth, symmetry, and a slower kind of beauty that keeps unfolding. Diamonds have a very high refractive index, boosting sparkle. Refractive index is the measure of how strongly a material bends light, and diamond bends it dramatically. When light crosses from air into diamond, it slows and changes direction more than it would in many other transparent materials. That bending is part of why diamonds can look bright even when they are small. It also sets up the conditions for light to reflect internally instead of escaping through the sides, especially when the stone is cut within certain angle ranges. This is the hidden reason diamonds can look lively under everyday lighting, not just under spotlights. The stone is doing optical work before any sparkle is even considered. It is guiding photons, redirecting them, and making the interior feel active. What makes this so fascinating is that the effect is not about decoration. It is an intrinsic property of the crystal, a built-in interaction between light and carbon. The diamond is not trying to shine. Its physical makeup makes light behave differently upon entering. That swaying, the bright presence that people can see across a room is made up of many different aspects. The polish of a diamond can be excellent, but its symmetry may not be perfect. Polish is about how smooth each facet surface is, while symmetry is about whether the facets are aligned and shaped in a coherent pattern. A diamond can have a glassy, flawless polish and still look off if the facet geometry is uneven. There may be a slight skew in the table. The cullet might sit off-center, or the crown facets might not meet in a crisp, repeating rhythm. The eye can pick up on these subtle differences, often senses them as a lack of crispness in the pattern of light and dark. Symmetry is what makes a diamond sparkle look organized rather than messy. It is also why, when viewed face up, some stones produce patterns that are sharp and pleasing, sometimes described as optical precision. Polish supports that by reducing tiny surface marks that scatter light, but it cannot correct a design problem. That is the fascinating part. This is where beauty becomes almost musical. The stone is not only bright, it is structured with repeating beats of reflection. When symmetry is strong, the diamond feels intentional, like it has a clean internal logic. When symmetry fails, confusion can set in on a smooth surface as well, and the light does not sing. The same way, diamonds can conduct heat extremely well, unlike many lookalikes. That single trait makes diamond feel less like jewelry and more like an escape artist for energy. Contact a diamond set into metal, and it can steal warmth so efficiently that it seems to run cooler than its surroundings. The reason is organized in the crystal structure, which lets vibrations travel through it with remarkable speed, carrying heat away before it can linger. Diamond has therefore found a second life outside of necklaces in environments where performance is ruined by overheating. Engineers use diamond as a heat spreader in demanding electronics, not because it looks beautiful, but because it behaves like a thermal corridor. It is also why a diamond can feel almost startling against the skin in a cold room. Even when it has been indoors all day, you are not sensing coldness created by the stone. You are sensing how quickly it pulls heat from you and shares it with everything around it, as if the diamond is refusing to keep warmth for itself. That heat conductivity helps gem testers separate diamond from glass. In a shop, the most convincing fakes often win by looking right, not by behaving right. A tester takes advantage of that by employing a small probe that monitors the rate at which the stone moves that heat away. Diamond clears it quickly, while many common simulants hold on to it longer, like a slow reply to a simple question. What makes this fascinating is how the test exposes the difference between appearance and identity. Glass can shine. Cubic zirconia can sparkle. Even under bright lights, carefully crafted materials can replicate the appearance. But when the instrument asks the stone to move heat, the imitation often hesitates. It is a quiet moment of truth based on physics rather than romance. Good testing also involves care because some materials can fool simple devices, and skilled gemologists use multiple checks to avoid mistakes. Still, the core idea feels almost poetic. A diamond reveals itself by how it handles energy, not by how it looks. It proves that beauty is only one part of what the crystal is. Except for some colored diamonds, diamonds are electrical insulators. Most diamonds do not let electric current pass through them in any ordinary way, which is surprising for something that feels so powerful and sharp. The crystal lattice holds electrons tightly, leaving little room for the easy flow that makes a metal conductive. That insulating behavior is one reason diamond has been used as a protective material in certain high-performance contexts where you want strength and stability without unwanted current. But the real intrigue comes from the exception. In rare cases, specific impurities or defects change the rules, nudging diamond towards semiconducting behavior. That means a gemstone can sit on a boundary, usually refusing electricity, yet capable of switching roles when its internal chemistry is altered in just the right way. It is not magic. It is structure. A tiny change in the crystal can rewrite how charge moves, turning a traditional insulator into a material that is closer to an electronic one. It also reshapes the idea of diamonds as purely decorative. Some are quiet guardians against current. Others become participants in it depending on what the crystal allowed inside while it grew. Blue boron diamonds can conduct electricity like a semiconductor. Boron is a small intruder with a big influence. When it slips into the diamond lattice, it can create pathways for charge carriers, giving certain blue diamonds an electrical personality that most diamonds never have. That is part of why these stones fascinate scientists as much as collectors. They are gems, with an extra layer of behavior hidden beneath the color. Semiconductor-like conduction means the diamond is not simply on or off. Under the right conditions, it can carry current in a controlled way, which opens doors for specialized electronics designed to handle high power and high heat. It is also a reminder that color in diamonds can be more than a visual flourish. The blue is a clue that something fundamental changed in the crystal's makeup. A few foreign atoms did not just tint the stone. They altered its relationship with energy and charge. This makes a blue boron diamond feel like a hybrid, part gemstone, part device, born deep underground, and yet speaking a language engineers understand. Diamond is transparent, yet it can be grown as black. Black diamond can feel like a contradiction, and that is exactly why it is so compelling. Darkness in a diamond often comes from how light is blocked, scattered, or absorbed inside the stone rather than from a simple coat of color. In a few cases, it is an intense concentration of inclusions and internal features that break up light until almost none returns clearly. In others, it can involve a dense network of tiny crystals or defects that turn transparency into opacity. The result is a gem that does not try to dazzle with bright flashes. It offers depth, a kind of quiet gravity. Cutters approach it differently too because the goal is not to showcase internal clarity but to shape surface reflections and silhouette, letting the stone read as sleek and deliberate. Black diamond also changes the emotional meaning people attach to the material. It moves from celebration toward mystery, from bright signal to dark statement, and it proves something important. Diamond is not one look. It is a whole family of behaviors, and transparency is only the version we are most used to praising. Carbonado. Diamonds are tough, dark, and often polycrystalline. Carbonado is one of the strangest. diamond varieties because it is not typically a single clear crystal. It is often a dense mass made of many tiny diamond grains fused together, creating a texture that can be porous and irregular compared to gem diamonds. That structure can make carbonado remarkably tough in the practical sense, resisting breaking in ways that differ from ordinary single crystal stones. Instead of one large lattice with clean planes, it behaves like a crowd. Force gets scattered across countless boundaries, making it harder for a crack to run straight through. Carbonado's deep black appearance and rough texture once made it feel less glamorous. But its story is fascinating. It does not fit the simple fairy tale of a perfect crystal. It feels more like a geological artifact, a material shaped by unusual conditions and then delivered to the surface as something already hardened by complexity. Historically, it has also been useful in industry because toughness and abrasion resistance matter more than sparkle. Carbonado invites a different kind of ore. It is diamond that chose resilience over dependence. Some black diamonds contain many tiny crystals fused together. Imagine building a gemstone from countless miniature diamonds pressed into one body, each with its own orientation, then locked into a single dark mass. That is the idea behind many black diamonds that show a granular polycrystalline nature. Under magnification, the surface and interior can reveal a mosaic of microscopic grains. And that graininess is part of what swallows light. Rather than letting light in, travel cleanly through, the stone repeatedly interrupts it, scattering and absorbing until brightness disappears. This internal patchwork can also change how the stone behaves during cutting and polishing. The cutter is not dealing with one uniform crystal. They are shaping a composite where tiny boundaries can influence how the material responds. That can make the finished look feel different too, more like a sleek stone than a window of brilliance. What makes this captivating is that it reframes the idea of a diamond as singular. A black polycrystalline diamond is a crowd solid, a gemstone built from many, carrying a complexity that you can sense even when it looks like pure darkness. Diamond can be made in laboratories using high-pressure methods. There is a method for creating the deep earth inside of a controlled box. High-pressure, high-temperature growth compresses carbon and heats it until diamond becomes the favored form, then uses a small diamond seed as a template for new crystal to build upon. It is not instant, and it is not fake. It is a human-made route to the same atomic structure that nature forms underground. This is so fascinating because of the shift in meaning. For centuries, diamond felt like a rare gift that only geology could succeed. High-pressure methods turn it into a material you can intentionally produce with controlled qualities that are appropriate for the jewelry industry as well. This does not erase the wonder of natural stones. It adds a second wonder, the idea that humans learned how to persuade atoms into the diamond arrangement on purpose. The process also creates its own signatures, which is why disclosure and identification matter in the market. Still, the emotional core is remarkable. The same crystal pattern that once required crushing mantle forces can now be made in a lab, not through imitating, but by repeating the conditions diamond truly prefers. Another lab method grows diamond from carbon gas layer by layer. Chemical vapor deposition feels almost like growing a crystal out of air. A chamber is filled with carbon gases energized, so carbon atoms break free and settle onto a diamond seed. Over time, the crystal expands one layer at a time, building a diamond with remarkable control over purity and shape. This method is fascinating because it behaves like a gradual building project rather than a sudden change. You can tune growth conditions, adjust the environment, and aim for materials suited to different purposes from gemstones to specialized technological components. It also changes the story of diamond from deep earth relic to engineered material. In some cases, CVD diamonds can be made with fewer inclusions and with properties tailored to electronics, optics, or cutting applications. But it is not simply about perfection. It all comes down to intent. CVD shows that diamond is not only something found, it is something cultivated. That idea can feel quietly mind-bending. A well-known crystal known for being born crushing pressure can also be assembled patiently atom by atom in a chamber built by people. Lay brown diamonds can be chemically identical to mined diamonds. This is where the conversation becomes wonderfully subtle. If you compare the basic chemistry and crystal structure, a lab-grown diamond can match a mined diamond because both are carbonate in the same diamond lattice. That means the difference is not a simple matter of real versus not real. It is a matter of origin and the small clues each route leaves behind. Natural diamonds often carry geological signatures tied to their formation environment, while lab diamonds may show growth patterns or trace elements that reflect manufacturing conditions. That is why gemological laboratories use sophisticated methods to identify origin, not because the material is different in a simple way, but because the history is different. For viewers, this is a powerful shift. Diamond becomes less of a singular category and more of a story you can trace. One stone, formed through Earth's deep processes and violent delivery. Another was grown by controlled human technique. They may have the same chemistry, but they are members of different narratives, ethics, and markets. The wonder is that atoms do not care about romance. They care about conditions. And humans now control some of those conditions well enough to make a diamond that nature would recognize as its own. Metal diamonds can show nitrogen patterns that reveal their history. Nitrogen does not always sit inside a diamond in the same way. Over long stretches of time, those nitrogen atoms can move and regroup within the crystal, shifting from single atoms to pairs and larger clusters. That rearrangement acts like a slow internal clock because it depends on heat exposure and time spent at depth. When gemologists analyze how nitrogen is arranged, they are not just measuring impurity. They are reading the diamond's thermal past, like finding out whether it lived in a warmer pocket of mantle or a cooler one, and for how long. It is a rare moment where a gemstone behaves like an archive rather than a treasure. Two diamonds can look similar from the outside, yet their nitrogen patterns can quietly announce that their life stories were nothing alike. One may have rested deep and warm for ages, allowing nitrogen to cluster. Another may have had a different journey, locking in an earlier stage. You can see the diamond's history, but you can't see it. Learn to interpret. Isotopes in diamonds can hint at where the carbon came from. Not all carbon is the same, even when it becomes diamond. Carbon atoms come in slightly different versions called isotopes, and the ratio between them can shift depending on the source. Some carbon signatures look more like a deep mantle origin than others, like carbon that once cycled through surface environments. When scientists measure these isotopic fingerprints, they can infer whether the diamond's carbon likely came from primordial mantle material or from carbon that traveled through oceans, sediments, and living systems before being dragged downward. It turns a gem into a kind of biography of an atom. The diamonds reveal more than just their shape. It is hinting at where its building blocks once lived. This idea can make you feel almost dizzy. A stone in a jewelry box might contain carbon with a story that began in deep earth chemistry, or carbon that once moved through a much shallower world, then took a one-way trip into darkness. Isotopes do not provide a single always respond, but they open a door to a world beyond sparkle. Some diamonds may form from carbon carried down by subduction. Subduction is Earth's slow swallowing motion where oceanic plates slide beneath continents and descend into hotter, deeper regions, along with rock. That process can transport carbon in a variety of forms, including altered carbonates, crust, and carbonary sediments that began as seafloor deposits. As that material moves downward, pressure and heat change its chemistry, releasing carbon-bearing fluids that can infiltrate mantle rocks. In certain conditions, that carbon can crystallize as diamond. The loop that it suggests is what makes this so compelling. Carbon that once moved through surface cycles can be pushed into the deep, transformed, and returned later as a gemstone that looks like it came from nowhere. The trip is not quick. It is a planetary relay race that can span immense time. This also reframes. Diamonds are a component of the carbon system on Earth, not a separate entity. A diamond can be the product of tectonic recycling, in which the planet sends carbon from its surface down and transforms it into something stable enough to withstand a violent ascent. A few diamonds come from extreme depths called super deep diamonds. All diamonds already feel impossibly deep, but a small subset pushes that idea further. Super deep diamonds form far below the typical diamond zone. And the proof often comes from what they carry inside, minerals that only stabilize at extraordinary pressures. These stones are like postcards from layers of Earth that are otherwise known mostly through seismic waves and indirect models. The wonder here is not just depth, it is access. Humans cannot drill anywhere near those regions. Yet a super deep diamond can deliver a physical sample from that hidden world into our hands. It can also show that carbon moves through the planet in ways that reach much farther down than many people imagine. The diamond becomes evident that deep Earth is chemically active, with fluids and reactions capable of building crystals under conditions that would crush ordinary materials. Super deep diamonds are rare, and that rarity makes them feel like exceptional messengers. They do not simply sparkle. They testify that Earth's interior has layers of complexity that can still surprise us, and that sometimes the planet accidentally sends us a piece of its most remote realm. Super deep diamonds can form in the transition zone inside Earth. The transition zone sits between the upper and lower mantle, and it is famous among geoscientists because minerals change structure there under pressure like matter-switching outfits. It is also a region that may store significant amounts of water locked inside certain mineral forms which can influence how rock flows and how the mantle circulates. When diamonds form in this zone, they become rare carriers of information from a place defined by transformation. Their inclusions can point to the pressure conditions of that layer, and they can hint at what kinds of fluids were present when the diamond grew. The fascinating part is that this zone acts like a boundary world, not surface and not deep mantle in the usual sense, but a middle region where the rules shift. A diamond born there is a product of that shift. A crystal formed where Earth is actively reorganizing itself at the atomic level. Holding such a stone means holding evidence that the planet's interior is not uniform. It has thresholds, and those thresholds can make objects that can withstand sunlight for an extended period of time. Some super deep diamonds might form even deeper in the lower mantle. Earth's lower mantle is huge and makes up a lot of the planet volume, and it is a place we understand mostly through vibrations, experiments, and careful inference. If diamonds form there, they represent an even rarer bridge between knowledge and touch. The conditions are intense with pressures so high that mineral structures differ from those near the surface and temperatures that demand extraordinary stability from any crystal. Evidence for lower mantle origins often comes from inclusions consistent with minerals expected at those depths preserved by the diamond's protective grip. The emotional punch is that these diamonds would be travelers from a region that shapes the entire planet dynamics, including how heat escapes and how mantle convection drives plate tectonics over long time scales. A diamond in the lower mantle is not just deep. It is from the engine room's deeper section. It suggests that carbon can crystallize into diamond under conditions that seem almost beyond imagination, then remain intact through ascent and erosion. If confirmed, each one is a physical handshake with a part of Earth no human will ever visit, yet which quietly influences everything we build on the surface. Diamond stability depends on pressure, not just temperature. People often assume heat is the deciding factor, but for diamond, pressure is the true gatekeeper. At sufficiently high pressures, the diamond arrangement of carbon becomes favored, meaning it is the stable form that carbon wants to be. Temperature still matters, but without the right pressure, diamond is living on borrowed time. This is why diamonds form deep and why the journey upward is so dramatic. As pressure drops, the stable identity of carbon shifts and diamond is no longer the form nature prefers. Yet, diamonds do not instantly change. The moment conditions change, they can persist as a metastable material like a perfectly built structure standing in a climate it was not designed for simply because change takes time. This idea gives diamonds a new kind of wonder. They are not only created by extreme conditions, they are sustained by a kind of stubborn delay. The stone you see in a ring is a survivor of a stability switch. A crystal that belongs to deep pressure world rules still present in our low pressure world. Because nature's transformations are not always fast. Near Earth's surface, graphite is the stable form of carbon. In the world we live in, Carbon generally prefers the softer arrangement we call graphite, with atoms stacked in sheets that slide easily. That is why pencils work and why graphite feels so familiar. It is also why diamonds are such an odd guest at the surface. They are not the form carbon typically chooses here, even though they can persist for a very long time. This contrast makes diamonds feel like visitors from a deeper set of roars. Graphite is stable at low pressures, which means if carbon were free to decide from scratch near the surface, it would not usually choose diamond. But once diamond exists, it can remain as a kind of holdover, a crystal trapped in its own structure. This also explains why diamonds can be altered by certain processes that encourage carbon to rearrange, especially under high heat. The key, the change in identity, is fascination. Carbon has multiple personalities, and the surface environment encourages one of them. Diamonds are the rare case, where a deep earth personality keeps showing up in a place where it is not the favored form. Like a stubborn accent that refuses to fade, diamonds survive at the surface because transformation is very slow. Why persist if diamond is not the most stable option near the surface? Have natural diamonds at all? The answer is patience, but not the humankind. Converting diamond into graphite requires atoms to break and reattach in a new pattern, and that rearrangement is sluggish under ordinary conditions. The diamond lattice is rigid, and without the right combination of heat catalysts or time at elevated temperatures, the transformation crawls. So diamonds can sit in river gravels, in rock, or in jewelry for ages without changing, even though the surface environment technically favors a different carbon structure. This creates a beautiful tension. A diamond at the surface is not the end of a narrative, it is a paused chemical possibility. It is stable in practice, because the pathway to change is difficult, not because the surface is its natural home. That makes each diamond feel like a preserved exception. It is a deep earth crystal living in a shallow earth setting, surviving because nature's rearrangements often happen on timescales that do not match our attention. A diamond can cleave along planes despite its famous toughness. Hardness makes diamonds resistant to scratching, but cleavage is about how a crystal can split when force strikes in the wrong direction. Diamonds have specific planes in their lattice where bonds can align in a way that makes it possible to break completely. This is why cutters plan so carefully. A diamond can resist abrasion for a lifetime, yet a sharp impact at an unlucky angle can cause it to chip or split. The drama is that the same orderly structure that gives diamond its strength also gives it directions of vulnerability. Skilled cutting historically relied on understanding this hidden map inside the stone, using controlled force to separate rough into workable pieces, then shaping with precision rather than brute strength for everyday wear. That's why settings matter, why exposed corners can be risky, and why certain shapes require thoughtful protection. The fascination is not that diamonds are fragile. They are not. It is that they are structured, and structure always comes with rules. A diamond is not an indestructible blob. It is a crystal with geometry, and geometry has preferred ways to behave when stressed. Cleavage makes diamonds risky to cut if struck the wrong way. The diamond's hardness is not a concern for a cutter. They respect its directions. Inside the crystal are planes where the atomic structure can separate cleanly if a force lands just right. In the workshop, that means one careless strike can undo months of planning in a single instant. Traditional cleaving was once done with a deliberate groove and a precise tap, a controlled gamble that could split a rough stone neatly or ruin it completely. Even with modern equipment, the danger has not vanished. It has simply changed shape. Pressure, vibration, and tiny stresses can travel through the stone in unexpected paths, and a hidden weakness can open where no one intended. This is why so much of diamond cutting is mental before it is physical. The cutter studies the rough, imagines the internal map, and chooses the safest path to beauty. It is a quiet reminder that a diamond is not just tough. It is organized, and organization comes with rules that must be obeyed. Diamond hardness resists scratching, but it does not guarantee strength. Hardness is about one kind of battle, the fight against being scratched. Strength is a different story. The ability to survive impacts, pressure points, and sudden shocks without cracking. A diamond is extraordinary at resisting abrasion, yet it can chip if struck on a vulnerable edge, especially in shapes with sharp corners or exposed tips. This surprises people because we talk about diamonds as if they are invincible, when in reality they are more like fine glass with a surface that resembles a fortress. Their stiffness can make them less forgiving under certain blows because the energy does not dissipate easily. It concentrates. That is why jewelers care about how a diamond is set, how high it sits, and what parts are protected by metal. It is also why someone can wear a diamond daily for years with no scratches, then damage it in one unlucky moment against a countertop or a door frame. The wonder is that nature built a material that wins the slow war of wear, while still asking us to treat it carefully in the sudden moments. The toughest diamond shape is not always the prettiest. Some cuts are designed to handle real life, not just showroom lights. A round shape has no corners to catch on things, and its curves help spread force, which can make it more forgiving during everyday wear. Meanwhile, shapes with sharp points like marquise or pear can be visually dramatic but physically exposed because a tip concentrates stress in a small area. Even a stunning princess cut, beloved for its crisp geometry, has corners that often need protective prongs. This creates a fascinating tension between engineering and aesthetics. The most glamorous silhouette can also be the most demanding, asking for careful setting choices and mindful wear. And the most durable outline can sometimes feel less bold to someone chasing a particular look. Choosing a shape becomes a quiet act of design philosophy. Do you want elegance that challenges the world or grace that blends in with it and endures? Diamonds make you answer that question with geometry, not words. Some inclusions create unique patterns collectors actually love. Not all collectors chase emptiness. Some chase signature. In certain diamonds, inclusions arrange themselves into patterns that feel like private artwork. Tiny constellations of pinpoints, delicate veils, or needle-like crystals that catch light in surprising ways. These stones can feel more personal because their interiors are unmistakable, like a face you would recognize again. Certain named effects have become collectible, like diamonds with aligned inclusions that reflect light like stars, cut in specific ways. In other cases, the appeal is simply rarity of character, a feature that makes the stone different from the clean, standardized look most people expect. This kind of collecting treats a diamond less like a status object and more like a specimen with personality. It also makes the diamond feel more connected to its origin because inclusions are evidence of growth conditions, not flaws. Added later, when a collector chooses such a stone, they are choosing story over perfection. The diamond becomes a conversation piece, not because it is flawless, but because it is distinctive in a way no other stone can copy. Fancy color diamonds are valued for strong natural color. A fancy color diamond is prized when its color is not faint, not apologetic, but confidently present. The grading measures how pure the image is based on hue, tone, and saturation. Color feels how light or dark it appears and how intense it is. What makes these diamonds so fascinating is that they shift the goal entirely. In a colorless diamond, people often chase the absence of tint. In an extravagant hue, the color is the treasure and the cut is chosen to show it, sometimes even at the expense of some brightness. The setting choices change, too, because surrounding metal can amplify or contrast the hue. Natural fancy colors also carry the excitement of scarcity because the conditions that create strong color are uncommon and the distribution of that color within a stone can be uneven or zoned in ways that make cutting a puzzle. A fine, fancy colored diamond feels like nature leaning into expression rather than restraint. It is not trying to be pure glass. It is trying to be unmistakable. Blue, pink, and red diamonds can be extraordinarily rare. Some colors are rare because the needed conditions are rare, and that rarity can make certain diamonds feel almost mythical. Blue and pink can already be scarce in natural form, and true red is among the most elusive hues in the world of diamonds. The market reflects this with intense collector interest, museum-level attention, and records that can surprise even people who know gemstones well. What makes the rarity feel different from ordinary scarcity is that it is not about one mine or one region alone. It is about the unlikely alignment of formation, history, chemistry, and survival through transport and cutting. Even when a diamond has the right color, keeping that color vivid after shaping is its own challenge. Because cutting can change how the color presents to the eye. This is why famous colored diamonds become characters in their own right, pass through history with names and reputations. A rare color diamond is not just a pretty object. It is a statistical anomaly that survived the Earth, survived discovery, and then survived the human decision to cut it. That chain of improbability is part of the thrill. The Hope diamond is famous for its deep blue color. Its reputation begins with a stone once known as the French blue, cut from an earlier diamond that traveled from India into the courts of Europe. Over time, it passed through royal hands, political upheaval, private collections, and finally into public view, where it became one of the most recognized gems on Earth. What makes it so captivating is that it does not rely on size alone. Its color is the headline, a saturated blue that feels almost impossible for a diamond. Paired with a history that keeps reappearing in books, museum halls, and late-night conversations. Stories have gathered around it the way dust gathers on old velvet, including dramatic rumors that museums work hard to separate from documented facts. Today, it sits as an object you can stand near, looking at the same stone that once moved through palaces, not as a symbol of mystery, but as a reminder that real history can be stranger than myth. The Cullinan diamond produced several major stones in the British crown jewels. It began as an enormous rough crystal discovered in South Africa, a find so large that it instantly became a problem as much as a treasure. A stone that size is not simply cut. It is negotiated with because one wrong decision can waste what cannot be replaced. The solution was bold. Expert cutters studied the rough for weaknesses and possibilities, then split it into many pieces, turning one discovery into a family of important diamonds. Several of those became famous in their own right, mounted into regalia and worn on occasions designed to project continuity and authority. The fascination is that the public often imagines a single legendary diamond when the truth here is multiplication. One stone became many symbols, each with its own shape, setting, and role. It is also a story about craftsmanship under pressure. The largest rough diamond ever found at the time did not become a single perfect jewel. It became a cascade of decisions, each one carving history into carbon. The cure has a long, contested history across empires. Its story is less about geology and more about what humans do with objects that carry status. Over centuries, it moved through powerful courts in South Asia and Central Asia, tied to changing rulers, shifting borders, and the rise and fall of empires. Different traditions name different chapters as the most important, and that disagreement is part of why the diamond remains so charged. Today it is associated with the British crown jewels, and its presence there continues to prompt debate and diplomatic conversations about heritage and legitimate ownership. What makes this diamond feel unique is that it is not only admired, it is argued over as if the stone has become a physical placeholder for history itself. Even its cutting history reflects changing tastes, with reshaping done to match the aesthetic expectations of a new era. The cower reminds you that diamonds are not born political, but they can become political when societies attach significance to them. It is a gemstone that carries not just light, but legacy. The Regent diamond once belonged to French royalty. Its path into legend began with discovery in India and a journey into European hands, where it was cut and named, then pulled into the gravitational field of French power. It was incorporated into crowns for a time and became part of the monarchy's visual language and ceremonial objects, where gems were used like punctuation marks in a sentence about authority. Then history turned, and the diamond had to survive the same turbulence that toppled the people who once claimed it. That survival is part of its quiet drama. Many royal objects are lost to time, melted down, stolen, or scattered. The Regent endured, moving through new owners and new political realities, eventually becoming a museum piece rather than a private symbol. Observing it in that setting changes the feeling. It becomes less like a possession and more like physical artifacts that outlived the system that elevated them, like evidence. The Regent diamond is fascinating because it shows how a gemstone can move from personal luxury to national story without changing its material at all. The Tiffany yellow diamond is one of the largest yellow gems ever cut. Unlike diamonds prized for icy whiteness, this one was chosen for its color, a rich yellow that reads as deliberate rather than accidental. Its size makes it notable, but the real achievement is the way it was cut to bring out that color, giving the stone a sense of weight and presence. Warm and unmistakable even without perfect lighting. Over the years, it became closely tied to a brand identity, appearing in exhibitions and special events as a kind of ambassador for what fancy color diamonds can be. It is not a diamond most people will ever see in person, yet it has a public life that many gemstones never achieve. That public life is part of the fascination. A diamond can be locked away. Alternately, it can be presented as cultural theater, a symbol that represents taste, craftsmanship, and aspiration all at once. The Tiffany yellow diamond also highlights how yellow can be celebrated, rather than judged, turning what some once called a tint into the entire point of the stone. Diamonds have been used as symbols of power for centuries, long before modern jewelry stores. Diamonds served as visual shorthand for authority, durability, and wealth that might be carried throughout the body. Rulers used them to announce status in courts where appearance was a form of politics and where a crown or brooch could speak before a person said a word. Diamonds also became tools of diplomacy, given as gifts meant to bind alliances or win over competitors because a rare stone can seem like a promise that can't be kept, easily matched. What makes this history so gripping is that the diamond's physical traits amplify the symbolism. A gem that is resistant to being scratched and holds its shine becomes a natural metaphor for permanence and control. Portraits, ceremonial clothing, and official regalia often leaned on that metaphor, building an image of unbreakable rule. However, the stones outlast the regimes that used them. A diamond can sit quietly in a museum, after centuries of being displayed as proof of supremacy, reminding us that power is temporary, that the objects used to advertise it can endure. The symbol survives even when the meaning changes. The modern engagement ring tradition was shaped heavily by marketing. The idea that a diamond ring is the default symbol of engagement feels ancient, but much of its global reach is modern. At the beginning of the 20th century, diamond companies had to deal with a real problem. They needed more people to see diamonds as essential rather than optional. Advertising stepped in to connect the stone with romance, commitment, and social expectation. And that message spread through magazines, films, and cultural repetition until it began to feel like tradition. The result is one of the most successful stories ever sold because it turned a product into a rite of passage. What makes this fascinating is not cynicism. It is the power of narrative. A gemstone that already had rarity and beauty was given a new role, and millions of people adopted it not because of geology, but because of shared meaning. Over time, the marketing became invisible, absorbed into custom. Understanding this does not erase the emotion of giving a ring. It simply reveals how culture is built, one repeated message at a time until it becomes the background of everyday life. Diamond cutting became a science of angles, not just craftsmanship. For centuries, cutting relied on trained hands and hard-earned intuition. But eventually, people started measuring things that the eye liked, like behavior. Studied and proportions could be calculated, which changed cutting from a purely artisanal tradition into something more in line with optical engineering. A key moment came when researchers analyzed how angles and facet relationships affect brightness, contrast, and fire, helping explain why certain shapes looked lively while others looked dull. That shift did not replace artistry. It sharpened it. Cutters could still make choices, but they could now justify those choices with geometry and light paths rather than only experience. This is why modern cutting often begins with planning, diagrams, and careful prediction before a wheel ever touches the stone. The diamond becomes a project, with constraints where every fraction of a decision affects how light returns to the viewer. The fascination is that beauty can be quantified without being reduced. The science does not make diamonds less romantic. It makes the Romance more precise, showing that sparkle is not luck. It is design. Laser. Cutting now shapes diamonds with astonishing precision. A rough diamond is often mapped in 3 dimensions. Before a cut begins, using detailed scanning to reveal its shape and internal features. That map becomes a plan, and lasers can then make narrow, controlled cuts that would be difficult or risky with older methods. The cutter's function is not lost with the laser judgment, but it expands what judgment can attempt. It allows complex shapes, cleaner separations, and more consistent results, especially while a stone needs careful handling to avoid wasting valuable material. Lasers also make it possible to add tiny inscriptions on the girdle, markings so small they can be used for identification without changing how the diamond looks to the naked eye. This combination of technology and tradition is what makes modern diamond work feel almost futuristic. The same crystal that formed deep underground can be shaped with beams of computer-controlled light that transforms an ancient object into something finished with modern precision. It is a meeting of time scales. The diamond is old, but the hands shaping it now encode machines that operate at speeds and accuracies no human could match alone. Tiny diamonds are used as abrasives in saws and drills. Most diamonds mined and manufactured are not destined for rings. They are destined for work. Small diamond grains are bonded onto cutting tools because they can grind, saw, and drill materials that quickly destroy ordinary abrasives. Concrete, stone, advanced ceramics, and tough metal alloys can be shaped efficiently when diamond grit does the scratching, especially in industrial blades and drilling bits. This is where the diamond's reputation becomes practical. It is not about sparkle. It is about endurance under friction, heat, and constant contact. The world around you is full of places where diamond has quietly touched the outcome. From construction sites that cut through rock to workshops that shape glass and precision parts.